Hello, welcome to another video. So on this one, our focus is on electric circuits, right? But this is from a Limpopo past paper, the Vhembe District, right? So on question 3 of this paper, we have this problem, right? A group of learners set up the apparatus to investigate the relationship between potential difference and current across the ends of a conductor R. Okay, this is our R, as you can see. Right, they closed the switch and then recorded the ammeter and the voltmeter readings. Okay, the experiment was repeated 3 times while increasing the number of cells in the circuit. All right, so this is like a clue. So what they're telling us there is, if they're increasing the number of cells in the circuit, it means the voltage supply was increased. So they were changing the voltage or the energy supply, if you want to call it using the fundamental principles of what it is. So now it means they were changing the voltage and then checking how it affects the current, and thereby they were able to tell the relationship between the potential difference, aka voltage, and the current across the ends of conductor R. All right, so this means they have to keep one of the physical quantities constant or one of the parameters constant, right? So in this case, they would have to keep R constant, whatever resistance R is, because they are investigating how changing the voltage or the energy supply affects the total current of the system. So they have to keep R the same. That's how experiments are run. If you change everything, you won't get meaningful results. They will be meaningless, basically. All right, so now we continue. This is the circuit, the experiment that was set up. Very simple. So it's just one resistor there, which in this case they decided to call it a conductor, but conductor and resistor, they are pretty much the same. It just depends on where the angle at which you are viewing it from. All right, so 3.1.1, the conductor used by the learners is an ohmic conductor, right? And then give one example of an ohmic conductor. Okay, before we give this one example of an ohmic conductor, I just want you to remind you, remember, an ohmic conductor, the reason we call it ohmic conductor is because it respects the principle of Ohm's law, right? So what usually happens is, remember, Ohm's law says the potential difference of voltage across a conductor is directly proportional to the current through it, of course, provided that the temperature of the conductor remains the same. So ohmic conductors respect that rule in a sense that as we change the energy supply in this circuit, this ohmic conductor will not have an abrupt rise in temperature. The temperature in the conductor will not rise so much such that it affects the relationship between the voltage and the current, and such that it affects that relationship in a way that the relationship starts being non-linear. So let me show you ohmic conductors. Okay, why am I changing? Usually behave this way, just as a quick reminder, right? So if this is my, let's say this is my current in amps, and then this is my voltage in volts, right? So if I want to plot how the voltage and the current are related. For an ohmic conductor, you will get a plot like this, a simple straight line showing the direct relationship between voltage and current, showing that voltage is directly proportional to the current. However, if on the other hand you plot the same thing but for a non-ohmic conductor, what you would get is something different, right? So for a non-ohmic conductor, you'd get a curve that looks something like this, right? So that's usually how non-ohmic conductors behave, right? The plots that you would get for a non-ohmic conductor compared to that one of an ohmic conductor are not the same, but you would be comparing the same things: voltage versus your current. You would find that for the ohmic, they are linearly related, but for the non-ohmic conductor, they are not linearly related. In fact, there's some exponential relation, right? Or is it an exponential? Yes. Or remember, you can also swap the axes. V can be on the x-axis, or it can be on the y-axis. They can be, right? So this is the difference. That's your ohmic conductor, and that's your non-ohmic conductor. This one does not respect Ohm's law, not Newton's law, Ohm's law. Okay, so that's the difference between these two conductors. All right, so that's one thing I wanted to highlight. And now let's come back and answer our question. We're asked to give one example of an ohmic conductor. You can find this in your textbook. There's quite a number of examples also out there, real world examples, but an example of an ohmic conductor is, one example would be what you call nichrome wires or conductors, depends which one. Let's use conductors in this word because the question asks for conductor. So a nichrome conductor is one good example. There are other conductors as well, like the manganese, but usually that's used for more sophisticated labs, and also stuff like your constant and so on, right? So, but nichrome conductor is the most commonly available one. Right, so that answers this question 3.1.1. And then after, we're told that a graph of their results is shown below. So the graph that they're referring to is this one that we have here. So these are the results that they were able to get, and they plotted the graph, and this is what we see. Okay, it might not be that clear, but this is the graph. Okay, if you check, it's a straight line graph, and which makes sense because they're investigating an ohmic conductor. Okay, so let's go to 3.1.2. For this investigation, name one variable that must be kept constant. All right, so for this investigation, name one variable that must be kept constant, right? So in an ohmic conductor investigation, remember what we're trying to prove there is Ohm's law. And then in such investigations, you would have to make sure that the primary variable that is constant, which is the most important one, is the temperature, right? Then the other variables, like the one I mentioned here, when I was reading this statement, remember I said they must make sure that the this resistor, the resistance of this resistor is not changed. So they must use the same resistor throughout. So that's variable number 2 that you must keep constant. But this question, you would prioritize temperature. So your most correct answer for this one would have to be temperature. The main reason being that is the primary variable that must be kept constant. It's the most important one, right? Because remember, that's the distinguishing factor or the difference between a non-ohmic and the ohmic conductor. So that's what sets them apart. So if the temperature is affecting your results, you might think, for instance, that you are investigating an ohmic conductor when it is in fact, you might think you are investigating a non-ohmic conductor when it is in fact an ohmic conductor. Right, that's of course just an extreme example. So in labs, what they typically do is to keep the temperature constant. For instance, you would switch off your circuits while taking your measurements down, okay, so that it doesn't heat up too much and then end up affecting your results. So moral of the story, 3.1.2, you must keep your temperature constant. Because even Ohm's law, it's there. We say potential difference is directly proportional to your current, provided that temperature remains constant. So that's why we are prioritizing temperature. Which physical quantity does the gradient of the graph represent? All right, so if we go to the graph and we check, right, our graph will always have, well, should pretty much always have an x and the y-axis, right? So now this is our x and this is our y, okay? And we know that a gradient is usually delta y over delta x, right? So let's check what we have for x. So for y, you would have your current, so you can say delta I, right, over, in x you have voltage, delta V in this case, and V, this is basically I over V. So does this represent something we've seen before? Yes. If you remember, our Ohm's law says the resistance is equals to the voltage divided by the current, right? The only difference here is that these things are swapped such that this, it's instead I over V, right? It means now, instead of being R is equals to I over V, because this is over 1, it means this is actually 1 over R and not just R. So the gradient then would have to be 1 over R, right? 1 over R. That's what the gradient is. That's what I over V would get you. It would get you the inverse of the total resistance, right? So our answer for 3.1.3 is simply 1 over R, right? So you can write it like this, and that's your answer, right? So it's easy to be tricked into saying this was simply resistance. However, that would have been true if V was on the y-axis and then our current I was on the x-axis. Then you could say that the answer is simply R. But in this case, you can't say that. 3.1.4, use the information from the graph to calculate the resistance of the resistor used in the investigation. Okay, so we know that the gradient will give us we will say delta y over delta x, right? Usually this is simply y2 minus y1, x2 minus x1. Okay, so let's go and check. We can take any of these 2 points. I usually prefer taking the first 2. So what we can do, we know that this is our x1, y1. That's point number 1. This is our x2, y2. That's point number 2. Remember, in a graph, we plot in x and y, right? So this point here, we can take out its x and y coordinates. So on the x, this point is on 0.6. So we can say x1, if we were to write it, for instance, it would be something like this. x1 is 0.6, because if you check, if we trace all the way up there, that point is in line with 0.6. And then now we have to go this side, right? That's our y now. So you have options here. It's either you count using the lines or the spaces. But what I prefer to do is I check, right? What's the difference between 0.2 and 0.4? That is 0.2. So this total space is 0.2. Okay. And then I count the number of spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So these spaces, they are 10. So which means this 0.2, it increases in an increment of 0.2 divided by 10, which means from 0.2 until 0.4, each space will be 0.02, right? So it's increasing by 0.02. As I move from 0.02 going to 0.4, I increase by 0.02. That means each of my space is 0.02, 0.02, and so on and so on until I get to 0.04. So that means space 1, I'll be on 2 plus 0.02, right? That's 2.02. Oh no, this is 0.2. So that is 0.22. And I keep increasing. So on space 2, I'm on 0.22. Actually 0.2 plus 0.04, because I keep increasing, right? Excuse me. So when I check my dots, it's on space 1 or line 1. So I'll take that as 0.22, because it's just here. Or is it on the space? Oh, it's on the space, sorry. So I'll take it as 0.2. It's hard to see from my picture, but let's use 0.2 for now. If it was on the space, I would say 0.22, because remember I said each space adds 0.02 from 0.2. So, and then I'll keep adding until I get to 0.4. Okay. So, but let's use this one. And then I go to x2, y2. If I check my y, I'm on 1.2, because I just draw a line straight down. I see that I'm on 1.2 here. And there, go all the way there, I'm on 0.42. Okay, these things are online. Okay. Sorry about this. Let's use it like that. And then 0.42 on my space. So this one is 1.2 and 0.42. Yeah, those are my coordinates. So let's write them here. So it goes from 0.6 0.22 all the way to 1.2 and 0.42, something like this. All right, so let us calculate now our gradient. This is x1, remember that's y1, this is x2, and then that's y2. Okay, y2 is 0.42 minus 0.22 because that's y1. Now x2 is 1.2 minus 0.6. So I will get that 0.2 divided by 0.6. It's 1/3 right there. Okay, should be. Yes, this is 1/3. Okay, so this is 1/r. Okay, 1/r is 1/3. So to calculate the resistance, we would simply cross multiply or flip it. Remember, if I invert the right hand side, I must do the same on the left hand side. So I can just do this if I want, and then I know that R is therefore 3 ohms, right? Because it inverts, it goes to R/1 is to 3/1. This is simply R is equals to 3. Okay, so that's our answer. R is 3 ohms. Okay, so let's continue. This is our 3.2. 3.2, we have a battery in the circuit diagram below that has a negligible internal resistance. Remember, this means our small r is 0 ohms. Okay, the resistance of the resistor R is unknown. Okay, when the switch is closed, ammeter or the voltmeter reads 15 volts, that's this guy, and then the ammeter A1 reads 1 amp. Okay, we see it there. All right, so 3.2.1, state Ohm's law in words. We just stated it on previously. So Ohm's law says that the potential difference across the conductor is directly proportional to the current, provided that the temperature stays constant or stays the same. That's it. So that's it. The potential difference across a conductor is directly proportional to the current in the conductor, provided that the temperature remains constant. So now that's how you would state it, and then these you would find it in your exam guidelines or your textbook. Okay, so let's go to 3.2.2. we're asked to calculate the current in ammeter A. Okay, let's check our resistor, our circuit. So before I answer, let me just trace our current, which is what I usually preach. So the longest line is this side, so current exits this side, goes there. That's our total current. Okay, enters the R ohm resistor. So this means the R ohm resistor will receive the total current. Okay, goes there. When it gets here, it splits. Now you have branch 1, so we'll have I1. Branch 2, we'll have I2. All right, so I2 in this case is simply 1 amp. Okay, then I1 here, I1 there. Why? Because these are in series, so they receive the same amount of current. And coincidentally, these two are actually, they have the same magnitude of resistance. Okay, so they mix here, then it goes again there. So that means the ammeter A reads the total current. Okay, then this thing, the current recirculates again. Right, so this is what we have, and then I can split it. I can get this to be my I1, and I make my I1 a different color, and I make my I2 a different color. All right, so now you can see what's happening. Basically, I have two currents for the two branches, and then yes, there are two colors. Right, so 3.2.2, we want the current in the ammeter or the ammeter. All right, so if you check here, we do know the total voltage supply. Okay, that's our 15 volts. But now we don't know the total resistance for this circuit, so we can't really use R. We can't really use R is equals to V over I, because we don't know R, and we can't calculate R at this point, right? Because only what we want is ammeter, and this mark allocation tells us that it should not take us a lot of work to find it, right? So now let's check. We know that the 6 ohm resistor receives 1 amp, right? But this is a portion of the total current. But how much does those 3 ohm resistors, how much do they get? Okay, so that's what we want to know now. All right, so if we check, we can sort of make the circuits to be like this, where we have 6 ohm and 6 ohm. The circuit is actually like this for the parallel combination, at least, right? We have something like this, right? And then it continues. Okay, so this thing is telling us that this branch is receiving I2, which is 1 amp. And we know that in a parallel combination, what usually happens is current divides, but the way it divides is it divides according to the magnitudes of the resistors. The resistors with the lowest resistance or the lowest magnitude of resistance, they get the highest current, and those ones with the highest resistance, they get the lowest current, because current prefers the path of least resistance. Okay, so what happens though if the resistances are equal? It means they will divide equally, so the current will divide equally. So what am I getting to? It means that when current got here, when current arrived here, and then it started dividing I1 and I2, it divides according, obviously, to the proportion of the magnitude, right? So since these are equal, it means they will divide equally, this current. So you'll get I1 and I2 being the same, so you get 1 amp here as well, and then they meet again here, they add up to form the total current. What does this tell us about the total current? It says the total current will simply be 2 times 1, which is 2 amps. Okay, let me write it more. No, not I2, sorry. The total current will be I1 plus I2, which is 1 plus 1, and this gives us 2 amps. That's the total current. Okay, that's it. So what does this tell me? I can say my answer will be I is simply I1 plus I2, and this is 1 plus 1 which is 2 amps, right? So your ability to answer this question dependent on your knowledge of the basic fundamentals of electric circuits, which is, well, current divides in a parallel combination, it stays the same in a series combination. Voltage divides in a series combination, it stays the same in a parallel combination. So those things, never ever forget those, right? So in this case, it was you understanding that. Okay, all right, so That's what happens. Now resistance of resistor R. Alright, so to find resistor R, how do we go about it? So there are multiple ways, but the one that I think is straightforward would be to say, let's see, it's 3.2.3. We know that if we take the total voltage supply and divide it by the total current, we would get the total resistance of the circuit. All right, but what is the total resistance of the circuit? It's given by R is equals to RS plus RP, right? And we say that RS is the resistor or is the series connection, which is just simply resistor R. That is R plus RP. RP now, we would get that it is 1/3, right? 1/6, and then we do that. Okay, so remember I explained this on our other video. So you add those resistors. You don't say, it's not allowed to say RP or the total parallel resistance is 1/3 plus 1/3 plus 1/6. This is incorrect. You can't say that. Right. So how you want to think about it is they must go in pairs. So if maybe there was another resistor here, maybe let's call it a 4 ohm resistor, then you could do that. You could say 1/3 plus 1/4, right? That's my first pair. And then 1/3 again plus 1/6. That would have been my second pair. So if I have two resistors in the branch, in the first branch, I would need two resistors again in the second branch for me to then do this. Otherwise, I combine the resistors such that I have an equal number in each branch, and then they are directly parallel, if that makes sense. So they are in pairs. So I can write the formula like this. But now I have two resistors in the first branch and only one in the second branch. So it doesn't make sense for me to use this formula like this. It won't give me the right answer. All right, so that's one thing you must remember. So we must combine these to form a 6 ohm resistor. So if I combine these two, I form one big 6 ohm resistor. Remember, that's usually what happens. Whenever you find the total resistance, what you are essentially doing is you are taking all these individual resistors and you are combining them into one big resistor, okay? Or one small resistor, depending on whether you are connected in parallel or series, right? So in this case, it would be one big resistor of 6 ohm because I'm connected in series for these two, right? And then now I can say 1/6 plus 1/6 and then do that for my RP. That's what I'm doing here when I'm adding these 3 plus 3. I'm saying I combined the resistors in branch 1 into 1. So this would essentially give me R plus 1/6. This should be what? 2/6, right? Like this, and then that's simply 3. R plus 3, okay? So this is my total resistance. My total resistance, let's call it R tot, right, is R plus 3. So the reason I'm calling it R tot so that I don't confuse my R's, because if I just did this, it makes no mathematical sense, okay? So it would confuse you with time as well. And in an exam, there's pressure and so many things. You might end up doing funny mathematical operations. Anyway, so that's what's happening now. Now what we can do is we can then go back to our equation and say this R tot, right, is V tot, right, the total resistance of the circuit is equals to my total voltage supply divided by my total current. That's what I'm saying. So now I substitute my things. I have R plus 3. What's my voltage supply? We're told that it's 15. Let's go and check it. This one, 15 volts, okay? So we can sub it here, and we just found our current to be 2 amps. So now I can say R plus 3 is 7.5, and then therefore my R is simply 4.5 amps. Sorry, ohms. Right, so that's what I get. There's another way of doing it, but I'll leave it to you to do it as homework, that one. All right, so this is the simplest way I think you would have approached this. And then now let's go ahead and go to 3.2.4. The total resistance in the circuit. All right, so this is 5 marks. In as much as I've already found this to be my equation for finding the total resistance, unfortunately I can't come now and substitute here and then say this is 7.5 ohms. Right, I have to recalculate it as if I didn't know that expression. The reason for that is this thing is 5 marks, okay? So if I do this, I doubt that I would get 5 marks even if they start marking from here. So yeah, I think the way it was set up, this question was a bit weird in this part, but let's try and assume that we didn't know that R. So the most basic way of finding the total resistance, we would go back to our formula and say R is equal to RS plus RP. Okay, we would say it like this. That's our R total. Now, and then let's leave this for now. We would say RS. Let's start with RS. It's simply this one resistor in series, which is my resistance R. I just found it to be 4.5 on our previous question. Okay, we leave that. Now what about RP? The total resistance for the parallel combination. We would say of course, let's use our, in case they have marks allocated for this. Right, and so on. Okay, so now we would say 1 over 3 plus 3 plus 1 over 6. This is 1 over RP. Then RP is simply 1 over 6. And this will give us 3 ohms. Okay, then now we say therefore R tot. Actually, there's a reason I cut that. Yes, there we go. Then now this is our R tot, which is 3. No, this is 4.5 plus 3. Then this gives us 7.5 ohms. Okay, this makes me comfortable that I would have gotten 5 marks, because first of all, they're gonna give me 1 mark for there, 1 mark for there, and maybe 2 marks here, something like that. Okay, but somewhere somehow they were gonna find my 5 marks, unlike if I just used my equation from here. But in an ideal exam situation, you should be able to use your previous equations or answers to your to answer your next question. So the way this one was set up was a bit strange because it didn't allow that. All right, even if it did allow, the mark allocation was gonna make you doubt that. Okay, so let's continue. Oh, now we are at 3.3. The resistor R of unknown resistance is now removed from the circuit. How will this change in the circuit affect the reading of ammeter A? Okay, so they now remove this resistor, that resistor R. Okay, so how will this change the resistance in this whole circuit? So it's very simple. You come here. Of course, numbers will not always be available, but whenever you have them available, you can use them to sort of answer these, I call them conceptual questions, because you don't need to calculate anything here. You just need to have an understanding of how Ohm's law works. But for some of you guys that prefer the numbers way, so in this case, what you would do, what they're saying is they removed this guy, because RS in this case represents our R ohm resistor. So if they remove this guy, when I calculate my total resistance, it means it won't, this guy won't be there. I keep saying this guy, but this resistor won't be there. So it means it would be 0 there plus 3, for instance. In fact, 0 won't even be, it'll just be 3. So if you notice now, the resistance drops from 7.5, the total resistance, to 3 ohms, okay? If I remove that R ohm resistor. So if I remove R ohm, my resistance will decrease. That's one thing. What happens if the resistance decreases? Think about it. What happens if I drop the resistance? What happens to the current? That's how you use, that's where now you use Ohm's law. Okay. So in simple, if I remove the R ohm resistor, the total resistance of the circuit will decrease, and therefore since resistance and current are inversely proportional, the current in the circuits will have to increase. So our answer here is simply increase. Why? The reason is everything I just said. All right, let's write it. All right, so that's how you would justify your reason. And then let's go to 3.4.1. The power rating on an electric stove is 1500 watts. Okay, if you want, you could always do that. All right, so what is the meaning of 1 kilowatt hour? So 1 kilowatt hour, what it means is if you had an electrical appliance that is rated at, so for instance, this stove is rated at 1500, right? In the case of 1 kilowatt hour, it means you have an electrical appliance that is rated as 1000 watts, and it is used for 1 hour, right? So if you multiply this to find just how much energy it consumes, you would get 1 kilowatt hour. So that's what it means. It's just a unit of electrical energy to help measure us how much an electrical how much an electrical appliance has consumed, right? So that's how you would answer. It's an electrical, let me just write it. It means so this is how you would say it. So it means that the amount of electrical energy consumed, or sometimes, or work done actually, or work done the work done by an electrical appliance with a power rating of 1,000 watts. Remember, 1,000 watts is equivalent to 1 kilowatt, operated continuously for a duration of an hour or 1 hour. Okay, so that's what 1 kilowatt means. 1 kilowatt hour means. It's just the energy consumed when a kettle or a stove or whatever has a power rating of 1,000 and that thing is used for an hour. Okay, so that's how we measure electrical consumption. So what the municipality normally does is they then charge you based on this measure. They say for every 1 kilowatt hour, we will charge you 2 rands or 4 rands or whatever. So if you think about it, it's like saying I am supplying you with buckets of water. Imagine my 1 kilowatt hour being 1 bucket of water. And I'm telling you that for every bucket of water that you use, I will charge you 10 rands. So what happens if you use 30 buckets or 30 kilowatt hours? So then I must take 10 rands multiplied by 30 kilowatt hours or 30 buckets in my example. And then I will get just how much you owe me. So that's pretty much how it works. All right, so yes. Now let's go to 3.4.2. So we are told that this stove is used for 4 hours and 30 minutes. So that's 4.5 hours in total. Right, so our time is 4.5 hours. All right, because 30 minutes is half an hour. Calculate how much it will cost to use the stove. All right, so first things first, you must find just how much energy this stove consumed, or how much work it had to do to convert the electrical energy into heat energy. All right, the work done by the stove. All right, so energy. First, we find energy. Remember these problems. Energy is equals to power times my time. I think they use T like this, but let's say delta T. Power times time is energy, right? Now, what is my power rating? Power rating is 1,500. But since we want it, once we start calculating costs, even our power must be in kilowatts. So we must convert this power to kilowatts. So what that means is my power is 1,500 years. This is equivalent to 1.5 kilowatts. Remember, watts to kilowatts we divide by 1,000. So that's what it is. And then now we substitute 1.5 here instead of 1,500 times my number of hours, which is 4.5. And then this will give me 1.5, 6.75 kilowatt hours. Right. So now I used 6.75 buckets of water. How much money do I owe you if you charge me? So how much it will cost you if you are charging me 2 rands and 37 cents for every bucket of water that I use. So we are told that 1 unit of electricity, 1 bucket of water, will cost us about 2 rands and 37 cents. So how much do I owe you as the municipality? So we say that cost usually in rands is equals to my energy consumed, which is in kilowatts hours, Must be careful with the units. The W is a capital letter, and then the other guys, the K and the H, are small letters. And then my tariff. Right, so the tariff is usually in rands per kilowatt hour. Right, so now this means I will say 6.75 times 2 rands and 37 cents. Right, so if you want, some people prefer writing it even with units included. And then you'd have 2 rands and 37 cents per kilowatt hour. And then this will give you the money, because this will cancel that and you'll only be left with money here. So this is 6.75 times 2.37. This is, I get 16 rands. I'll just say this is 16 rands because it's 15.9975, and usually we round off money to 2 decimal digits. So if you try to round off here, you just go to 16. Okay. All right, so why is it cancelling that? Because remember, anything that is per means you are dividing there. So if I were to write this mathematically, I would have 6.75 kilowatt hour, right, times 2 rand.37 per kilowatt means I'm dividing here like this. So this is a denominator. So if you check, this is over 1, this goes with that, and then that's why. All right, so this is it for this particular question or this particular problem, and I'll catch you on our next video.